Welcome back. Example 3 says find the volume of the solid generated by revolving the region bounded by the following lines and curves about x equals 2. X equals 2. Now figure 5 shows a setup of this, but you'll want to remember x equals 2 is a vertical line at x equals 2. A lot of people mistakenly switch around the vertical and the horizontal lines. Be careful not to make that mistake because it throws off the whole problem. And so you want to make sure that when you draw the axis of rotation, double check that. Double check that. Make sure that you know that that's a vertical line in this case. Or if it were y equals something, that it's a horizontal line. Now our region is bounded by y equals x minus x squared and y equals 0. Now one thing is, if you didn't know what the picture looked like, then you would have to draw the picture from this information. So one of the things that you would want to do to figure out where your region is try to figure out where these two curves intersect. So where does the y equals x minus x squared intersect y equals 0? Y equals 0, you know, is the horizontal line along the x-axis. Y equals x minus x squared will be a parabola that opens down because of the negative in front of the x squared. And so probably, I mean, if it opens down, it's got to have its vertex above the x-axis if these two things are going to be intersecting each other to create a region. But to figure out those intersection points, what we could do is, let me do it right here. Intersection points. Again, this is if you don't have the graph, like we have in figure 5. So if you wanted to find the intersection points, you would set these two equal to each other. You could factor out an x, and you would get x equals 0 and x equals 1. So this corresponds with 0, 0 and 1, 0. The y values are 0 because here we have y equals 0 for, and we're looking at the intersection between these two, so the y coordinate has to be 0 in order for you to have an intersection point. Okay, so the main thing is these are the intersection points, so you could put a dot here and a dot right here at 0, 0 and 1, 0, and then you would just draw a parabola that's opening down. You don't necessarily have to find exactly the vertex, although you'll know that it's halfway in between at an x value of a half. And you don't really need to know what the y value is unless something else compels you to need to know that. But unless you need to know, you don't really have to draw that information. And here it turns out we're not going to really care about that. So let me erase those 2 points. And so we would be able to draw this little region. Now we're revolving about the x equals 2, and I said to definitely do this as soon as possible, so we'll remind ourselves that we're revolving about the x equals 2 line, although if you draw a separate axis, it's kind of clear what you're going to be rotating about. And so we're going to draw a shadow copy of that region over on the right side of the axis. If you took that region, revolved it all the way around the axis, it would end up right here. Again, optional, but good for visualization. And we are going to make if we're going to use our shell method, we're going to make our rectangles parallel to the axis of rotation. Shell method is going to be parallel rectangles to the axis of rotation. That's the only way to make it so that you have shells. There we go. Not the prettiest shell, but it'll do. It doesn't even get to this. Here, let me fix this here. There. It's like 0.01 better. All right. So there's our sample shell. Now we're going to have to figure out the radius of this shell and the height of the shell. Now the radius of the shell is going to be the distance from our rectangle to the axis of rotation. It's that horizontal distance. Let me just draw that here. It's this horizontal distance. That's the radius of each of the shells. Now to get a horizontal distance, we're going to subtract the right x value minus the left x value. Right x value minus the left x value. Well, on the right, we've got x equals 2, right? That's the axis of rotation. On the left, we've got an x value of just x. So we'll have 2 minus x. Notice, by the way, that I used the original region, and so the rectangle that was in the original region. I didn't use this rectangle over here in the shadow copy of the region. I used the original one. That's what you'll always want to use. Otherwise, you might end up with something like x minus 2, which is not exactly what the radius is going to be. Radius will be 2 minus x. It's the bigger x value, which is 2, minus x, which is the smaller x value. The x values are going to range from x equals 0 to x equals 1. That's where those x values will live. They won't live over here in the x values from 3 to 4, because this is where our region is. It's from x equals 0 to x equals 1. Okay, now for the height of this cylindrical shell, well, that will be this vertical distance, which is going to be the y value on top, given by the formula x minus x squared, and then minus the y value on the bottom, which is y equals 0. So you have, did it again, x minus x squared, and then minus 0 if you want, but you don't have to write that. So this is actually the top, and then the minus the bottom is minus 0. So I'll just write this whole thing is the top. You could put minus 0 like the bottom if you wanted to, but I'm not going to write that part. Actually, I'll just leave it in there, whatever. Make decisions on the fly. Executive decision. Okay. I'm the farthest thing from an executive. So we're going to feed this radius and height into the shell integral. Now the integral is going to go, as we talked about just a moment ago, from x equals 0 to x equals 1. That's where your x values are going to go across your region. Then we're going to take the 2 pi times the radius, then times the height, and dx, again because our rectangles are vertical, so we're going to integrate with respect to x. That's why everything here we did was in terms of x. Okay, feeding in our radius and our height. Once again, we have a fairly straightforward integral. Make sure that you distribute everything here. You're going to have to FOIL 2 times x, 2 times negative x squared, and then negative x times x, and then negative x times negative x squared. So you'll get 4 terms, and you can pop the 2 pi out. And if you have trouble with this, just let me know. And in the end, you should get pi over 2 for your result. Now, there's one more thing that I wanted to mention about this example in particular. We said at the very beginning that sometimes the washer or disk method can be very difficult. It can be very difficult to use that method. This is an example of that. If we tried to use the washer or disk method, let me just draw a little picture of our region. If we tried to use that method, we would have to make our rectangles perpendicular to the axis of rotation. So if our axis of rotation was over here, right? I'm just drawing a picture of figure 5 with some of the basics. So if we're rotating about this line over here, and we want to use the disk or washer method, we would make our rectangles perpendicular to the axis of rotation, because then we would generate these kind of washers. It's probably good that we have this drawn here, because you can see how washers are really, really flat. Shells are not flat, right? Washers, though, are infinitely flat. So if we tried to set this up, we could draw a picture of it and everything, but the problem would come when we're trying to find the inner and the outer radii. The problem comes when we have to find the x value along this curve for the inner radius and the x value along this curve for the outer radius. To find those x values, we would have to take y equals x minus x squared, and we would have to solve for x. So we would have to solve this for x, but that's like a quadratic. We would have to use the quadratic formula, which would start to look really ugly. And so this is going to be very difficult to set up. You could probably do it because you have the quadratic formula, but it would be a really nasty looking setup. So much easier with the shell method in this case, because all you end up with in your integral is just this little polynomial. So here, note that the washer method, or cross-sectional method, is difficult here. And the problem is because this solving for x is tough. I mean, again, quadratic formula, so not too tough, but it's annoying because you have to then decide which side of the, you'll get a plus or minus in your quadratic formula. So you have to decide, is this one the minus one? Yeah, that's probably minus one. This side is the plus one. But anyway, more difficult with the washer method, much easier with the shell method. So in summary, for volumes of revolutions, this only really the disk/washer method and then the shell method, these two are only talking about volumes of revolution. So the summary is that the washer or disk method is going to, you're going to use that method if you make your rectangles perpendicular to the axis of rotation, and vice versa. And then the shell method is what you're going to use if you make your rectangles parallel to the axis of rotation. Now, which one to use? Sometimes you'll be given a choice about which method you want to use, and oftentimes on tests. And so which one you use just depends on which is going to be easier. If you are starting to use the washer method and you're running across a problem here like, ooh, I don't really want to solve for that, that looks a little bit difficult, then you could try the other method. Just try changing it so that your rectangles are parallel to the axis of rotation. Or if you're trying to make your rectangles parallel to the axis of rotation and using the shell method and you're running across some difficulties, just try using perpendicular rectangles. So some of it's just a trial and error kind of thing. That's all for this video. Thanks so much for watching, and see you next time.